Okay, so this is chapter 13, lesson 2. The first question is, which of the following compounds will have two absorptions with the integration ratio 1 to 3? So here, this is going to go back to a concept from the last lesson, right? These are connected by carbon-carbon rotation, right? So CH3, the reason CH2 isn't included is because it's CH2 chemically totally different. Okay, and even if it was CH3, it still wouldn't be the same because it has that bromine attached to it. So this would be all together, okay? That's one signal. This is the second signal, okay? So then we want the ratio. So the ratio, purple is 2 protons, right? And this one, it's all together, so it counts as one whole. So this is 3, 6, 9. The ratio would be 2 to 9, which we see right here, right? The purple is 2, and the one whole signal, these are by signals, right? You're not going to do them by individual protons. They're not going to be 3, 3, 3, 2. Okay, because this is all together, this is one signal, they're going to be counted as 9 together. This one, take a look at it. These connected by carbon-carbon bond rotation, they are one signal. This is the second signal, and we see that right here, right? We have the one signal is counted as 1 altogether. That's 6. The other one is counted as 2. This is 3 to 1 ratio. The last one is going to be all of these counted together as 1. And again, they are, the only difference here was that this was, like for example, this is 3, right? And this is BR. Here, oh my god, here we see exactly that. It's pretty much flipped, right? We have CH2 BRs with a outlier of CH3. Even if this was CH2, it would still be different because it doesn't have that bromine attached to it, okay? So we're counting this as one signal, and we're counting this as the second signal, meaning we get our answer for this one. This one signal one is 6 because it's 2, 4, 6, and then the second signal is 3. So those are the protons, okay? So I want you to remember signals, individual, sorry, my Apple Pencil isn't calibrated right, protons. So signals, individual protons together, each. Okay, so now we move on down here to multiplicity. So this is where we have that Pascal's triangle. I don't know if you know how to do it, but I'm going to assume no, and I'm going to teach you it, okay? It's really easy though. But if you know how to do it, then that's really, really good. So the number of neighbors, right? That's going to be n plus 1. So let me see. Yeah, we'll get into neighbors in a little bit. So n plus 1, actually no, we can get into neighbors right now. This, because this counts as 1 altogether, we're going to say that n plus 1, right? This is going to be, hello? N plus 1 neighboring protons, okay? The 1 is going to stand for which signal you're using. So if we're going to be using pink, we're going to be using this signal right here. We're going to say that that's 1 plus how many neighboring protons there are. And there are 2 neighboring protons from purple. So 1 plus 2 is going to equal 3. So this would be a triplet. Now if we do that for purple, we're going to have 1, because keep in mind, 1 is always going to be whatever you're going to be calculating. The neighbor is going to be the pink. So we count 1 plus each of these. Okay, we don't just count it as 3. We still count them as 9. So 1 plus 9 equals 10. And that's whatever that is. Okay, so that's going to be what? 10 tet or something? I don't know. But that's how that works. Okay? So, and like over here, the neighboring, like the signal for this one would be 1 plus 6. Because there's 6 yellows, right? And that's going to be a septet. Oh my goodness. Oh my goodness. Here, our neighbor for this one, right? We do 1 plus how many neighbors there are? 2, 6, 8. Plus 8 equals 9. That's how many signals this one is going to have. Okay? But if we do it here, this whole thing is going to be the 1 plus how many neighbors it has, which is right there. That's 3 neighbors, 4. This is going to be a quartet. So that's how the n+1 rule works. Okay, now we can move on to here. So we have 0 neighbors. That's going to be n+1, which is 1. The multiplicity is going to be a singlet. The relative intensity is going to be a 1. And the shape is just going to be up like that. Now, the number of neighbors is going to be 1. n+1 is 2. There's going to be a doublet. And you're going to get 1 to 1. And that's going to be equal. Now, this 1 to 1 tells you that it's going to be equal. That the heights for this will be the same. Okay, that 1 to 1 ratio will tell you that the heights will be the same. Next, 2 neighbors, 2 plus 1 is 3. That's going to be a triplet. You're going to get 1 to 2 to 1. This means that these two are going to be equal and this one's going to be the highest. So it should look like that. Okay? And it does look like that. See? Now we have 3 neighbors. 3 plus 1 is 4. We're going to get a quartet. We're going to get a 1 to 3 to 3 to 1 ratio. This is telling us, again, same thing. 1, 2, 3, 4. Okay, this is telling us that these two are going to be the same and these two are going to be the same. But this is going to be higher in frequency. And that gives us this right here. Next is 4 neighbors. So 4 plus 1 is 5. It's going to be a quintet. And then we get a 1 to 4 to 6 to 4 to 1 ratio. This is telling us the 1 and 1s will be the same height, lowest. 4 and 4 same height, second lowest. 6 will be on top, and it's going to be the highest peak. And that is exactly what we see. This is the 1, 4, 6, 4, 1. Okay? Next is 5. 5 plus 1 is 6. This is a sextet. It's going to be a 1 to 5 to 10 to 10 to 5 to 1 ratio. 1, 5, 10, 10, 5, 1. Okay? Same, same, same. Highest, highest, second highest, lowest. And that is exactly what this is going to look like. Pascal's triangle, I can go through it fast, and then if you need more help, you can ask me. But I'll assume you don't know how to do it, but if you do know how to do it, then just skip, you know? So 1, we go down, it's going to be 1 to 1. Now, we start writing it as 1. we add these two, we get 2, and we end it off with a 1. We go down with a 1, we add these 2, we get a 3, we add these 2, we get a 3, and then we go down with 1. You go down with 1, you add 1 plus 3, 3 plus 3, 3 plus 1, 3 plus 1 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and you get a 1. You keep going down, that's going to be a 1. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 6 plus 5, 1, 4 plus 1 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and we end up with a 1 right here. Okay, so the whole thing is that it's just going to be adding each other until it gets these. And you can double check this by making sure that there's 6 values, right? This is 1, 2, 3, 4, 5, 6. Again, 1's here. 4 plus 1 is 5. 4 plus 6 is 10. 4 plus 6 is 10. 4 plus 1 is 5. You just keep going like that. Next, oh Lord. So this one, honestly, all you need to know from this is OH and NH together make a broad singlet. And a broad is just going to look like that. This whole thing, it's just a rapid acid catalyzed proton exchange. And like why it happens. So OH and NH groups undergo rapid acid catalyzed proton exchange in the presence of a trace acid. Complete the proton exchange mechanism. So the nucleophiles are going to grab the electrophilic base. It's going to bring that over, and see, I don't fully understand it, so I'm not going to go fully into it, but you don't really need to know this because we did not see this on the exam at all. Protons transfer over in HB. However, we should know how this happens. So how does a rapid proton exchange result in a broad signal? So this results in averaging of the splitting because it's happening so fast that the splitting that's occurring between them is going to be averaged out. So it yields an average broad singlet. Okay, so instead of being like this, for example, it's just this whole thing like that. So, and OH and NH protons do not split neighboring hydrogens. Either way, I think of that, I think of O's and H's kind of like a carbon. So, for example, if OH is right here, and you have a carbon with a hydrogen attached. Generally, if this was a CH, right, we could say that, oh, this is 1 plus 2 is the neighbor, and this would be a triplet, right? However, when we're doing an H, and we go over and there's a C and an H, and let's say 2, since I used 2 in the other one, then I would say, look at it, right? There's no carbon attached to it, so it can't move forward to the other carbon. Because whenever we see these, there's always a carbon attached to the hydrogen, and that way we're able to do the neighboring. But that nitrogen, or when there's an oxygen, it's going to be preventing it from going forward to that carbon to have a neighbor. So that's why they're not going to be splitting the neighbor. So next we have why do aldehyde protons appear as sharp singlets despite having neighboring protons? So in your worksheet, it's going to be written out as like this with an H right there. But it took me a second to understand what they were saying with that because it's whatever. But pretty much this is a... okay. So I'm going to color this as CH, right? And then this is saying that coupling constant, the coupling constant, remember, which is measured in J, is so small that it's not even observed. So aldehyde hydrogens do not split the neighboring hydrogens because the distance between this is so tiny that we don't really care, right? We don't care to split it because the distance between them is so small, so we might as well just call them singlets and move on with it. So next is number 4. Determine the multiplicity you would expect to see for each bolded hydrogen in the molecule below. So you're going to draw the shape of the signal on the line provided below the molecule. So we're going to start with H3, right? This is the one we want to know the signal for. So remember, we use N plus 1. So the plus 1 is going to be coming from this. From the H3, we'll always do 1. The neighbor is going to be the carbon and the amount of hydrogens attached to that. And keep in mind, if this were to be in CH3 and they were the same, we couldn't do neighbors, meaning the neighboring would be 0. However, we have one neighbor. So for this, N plus 1, we would do 1 plus 1 equals 2, which is a doublet, right? We can double check that, N plus 1 and 1 plus 1 is 2, doublet. Next, this H. Remember what we said before up here, OH and NH appear as a broad singlet because, results in averaging of the splitting and yields average broad singlet. So this is just going to be a broad, and it's going to look like that. Next is this one, okay? So we have this hydrogen, and listen, I was done with it, and I got confused. I was like, wait, if this is hydrogen and this is carbon, that means that we can't do this carbon because they're too far. But that's not how it works. This is actually CH right here, and that's what I drew here, is that it's CH carbon, meaning yes, we can do that. Like, it's not far. It's not far from one another. So we have the CH, remember, N plus 1, neighboring, right? The plus 1 is going to come from this. Neighboring are 6 carbons, okay? So it's going to be N plus 1, 6 plus 1 equals 7. So that's directly bonded. It's going to be a septet. N plus 1, 6 plus 1 is 7, septet. And let's look at how, like, it's supposed to look, okay? Because you know how we have to have the specific kinds of signals? You could write it down on your note card, but again, my thing is, we have minimal space on our note cards, so I feel like it's just good to remember these things. Again, we use our Pascal's triangle. 1, 1, 1. 1, 1 plus 1 is 2, 1. 2 and 1, 3. 2 and 1, 3, 1. 3 and 1, 4. 3 and 3, 6. 3 and 1, 4. 4 and 1, 5. 4 and 6, 10. 6 and 4, 10. 4 and 1, 5. Now we need 7, because our signal is a septet, right? That is our signal. 1, 5, 6, 5, 10, 15, 10, 10, 20, 10, 5, 15, 5, 1, 6. This means that we have these two are the same, these two are the same, these two are the same, this peaks. So 1, 6, 15, 20, 15, 6, 1. 1. And that is what we see right here. Right, there's a total of 7 peaks. 1, 2, 3, 4, 5, 6, 7. The 1s are the same, the 6s are the same, the 15s are the same, the 20 peaks. Okay? Next is this problem. The 1H NMR spectrum of each compound below displays 2 signals. The magnitude of the coupling constant, JAB, match these structures. And remember, these are how far they are, right? The coupling constant is how far the couples are from one another. Off rip, you can look at the trans. The trans is going to have the largest, so that's going to be 15. Because they are trans from one another. They are going to be the farthest apart. And again, that's true. That's 15 HC. And you draw the 2 peaks, right? Because it is neighboring. So this is a CH bonded right here. So we're going to take 1 plus just 1h. So all of these are going to be doublets, okay? So the way we write it is like this. And we say that there's a distance of 15 between HA and HB. Next are going to be the 10, 7, and 2. So let's start from this one. Do you remember our vicinal and geminals? Well, this is a geminal, okay? It is right across from one another. There's a difference of 2 sigma bonds, and that's not a long distance. That's very short. So we know that this is going to be our shortest one, which is 2HC. So geminal, difference of 2 sigma bonds away, 2HC, and so our signal looks like that. It's 2HCs away. And so, yeah, let's go here. This is our, okay, we have now these 2 left. The way I like to think about it is by hybridization. This one, 1, 2, 3, right? So it's going to be sp2 hybridized, this carbon, meaning the bond angle is going to be, what, 120? 3 bonds, yeah, 120 degrees. 120 degrees. Before we reveal anything, hold on. Let's go over here and look at this one. This is 1, this is 1, 2, 3, 4. That's going to be sp3 hybridized. Okay, and sp3 hybridized means it's going to have 109.5 degrees. Yeah. Ooh. Don't look at that. I'm dumb. I don't know why I put that. Let's just erase. Yeah, pretend you didn't see that. So sp3 is 100. Oh my God. It's 109.5 degrees. Okay, that's all we're looking at right now. When you have these 2, right, we have one that's 3 bonds and 120 degrees apart, and then sp3, which is 109.5 degrees apart. These, because it's a smaller angle, means that these are going to be closer together, right? So this is going to end up with the second smallest, so it's going to be 7HC, and that's going to be that distance. This one, on the other hand, has a bigger angle between them. This one has the smaller angle, this one has the bigger angle. So if it has a bigger angle, then there's going to be more distance, right? So this one is going to be 10HC with a distance of 10. And I forgot to that one, but yeah. So next we have this one. So acetylene reactions with 1 equivalent of HBr to form 1 bromoethene. Will the HA signal be a quartet or a doublet of doublets? So we can start off by looking at JAB, which is equal to 14, meaning our spectrum, our tree, is going to start by splitting JAB first. Okay, so our main one is HA. And remember, when we write AB, it's A being split by B. Okay, so we can start this off, and again, what's it called? Red corresponds to the starting, HC is going to be the green, and then HB is going to be this one. So because JAB is the biggest, that's what we start our split off by. So we split it into 2. We split it into 2 because, what's it called? JAB, the constants are, for JAB, we still use the same rule, n plus 1. So n is going to be this 1. 1 plus 1 equals 2. So that's why we split it into 2. And the distance between these is 14, because that's what we're told up here, right? It's 14. Then we go ahead and do JAC, which is going to be, again, let me just write n plus 1 up here. Our neighboring, our C, is 1, right? So we do 1 plus 1 of the HA itself, and we get 2. Okay, let me just do this in red. Sorry. 1, 1. Okay, so this one right here, we have split it. This is JAB, jab. A being split by B. And A is just 1 right here. So we split it into 2 because that's what our signals tell us to do. Next, we have to split these, right? So we split JAC next because JAC has the smaller one, smaller distance. So we already have these split by B. Okay, so this is 2 up here, 2, 2. Next, we have to split it twice more. So as we follow our tree, this is our HA. We split it into 2 because of the B, and now we're going to split it into 2 again because that is what the signal is telling us to do by, C. And then the distance between these is going to be 2. And we know that because JAC up here is 2HC. Okay, JAC is 2. I don't know what this says. Oh, so it's going to be a doublet of doublets, of doubles. Okay, doublet of, no, yeah, that's wrong. So doublet of doublets. Oh Lord, whatever, you know what I said. So it's going to be a doublet of doublets. If it were to be a quartet, it would have just been like that. However, we're not going to see that. When I reveal this, it's going to look, hold on. It's going to look like this because both of them are doublets. Okay, let me redraw. So this one right here is a doublet. And these down here were technically doublets as well, right? Because that's what we were told here, is that these are going to end up as, sorry, my pen is not calibrated, doublets, okay? So that is why in our spectrum, when we draw it, for example, right, this is our, well, hold on, HB, 1, 2, 1, 2, 3. Yeah, so HB is going to be on the higher frequency side. So this is our first doublet. The distance between these is 14. And then this is going to be our second doublet. And the distance between these is 2, I believe. So, and we know that this is the right answer because in the end we have 1, 2, 3, 4. Right, and we end up with, oh Lord, oh my God, and in the end we do end up with 4 peaks, right? So yeah, that's that. Next, so the 2 isomers both have 3 signals in the 1H NMR spectra. Circle the isomer which corresponds to the 1H NMR spectra. Provide a brief explanation of how you came to your conclusion. This one is literally just looking at and finding out what goes where, okay? Let's start with the bond that's going to be the closest to the bromine and the most de-shielded, which is going to be the hydrogen. If something is very de-shielded, we know that it's going to be on this side, right? So this one has to correspond to what's right here. So let's proceed, right? We use the same rule, n plus 1. 1 is going to come from this hydrogen. The n neighbors are going to come from the ones that are directly on the next carbon, right? So that's going to be 2, 4. So 1 plus 4 equals 5. And that is a quintet, and that is exactly what we see. So far, this is right, okay? Next, we're going to see, oh, damn, I should have, okay, it's okay. Next, we're going to look at this one, because this is the second one that's the farthest from the bromine, meaning if this corresponds, this should be equal to whatever is under here. So, because these are the equal signals, we're going to be looking at 1 plus 3, and this 1H here. So 1 plus 3 plus 1, that's 5. this has to be a quintet. And that's exactly what it is, okay? So quintet right here, it corresponds. Last is the triplet. So again, this is n plus 1. This has to be our 1, right? So this is 1 plus our neighbors, 2 equals 3. This is a triplet, and it works. So our very first one ended up being the correct one for our for the problem. Okay, and I drew it here as well, because you should be able to draw it. You have to start with the highest frequency, and that's what this was. Highest frequency right here, quartet 1, 2, 3, 4, 5. Then the second highest, quartet again, and then the triplet. So next is this one. We obviously know that this one is wrong because this one was right, okay? But we can still look at it. So bromine, this one is going to be our most deshielded because this is a CH3 and they are both 2 bonds away. Right, that's 2 bonds, this is 2 bonds. So our CH2 is the most deshielded. So this is going to be n plus 1, which is 1 plus the neighbors, 3, 6. Whoa. Yeah, no, okay, sorry. 1 plus just 3, because keep in mind that carbon is right here. This carbon has no hydrogens attached to it. So we don't use this because this carbon is attached to this carbon first, not directly that carbon. So the only neighbor this one has is CH3. So 1 plus 3 equals 4, which is a quartet, and either way we know that that has to be wrong. Because if this is our highest frequency, and we're saying that on this spectrum, this is the highest frequency, and this is a quintet, that's wrong. Because this is a quartet, okay? So, quartet. And again, I used Pascal's triangle. This is a 1, 1, 1. 1 plus 1 is 2. 2 plus 1 is 3. 2 plus 1 is 3, okay? Let me grab the eraser so I can, and that's the highest frequency. That's what that's supposed to look like. Okay, so let's go to the second highest frequency next. And we knew already, because we said this is 2 bonds away, this is 2 bonds away, meaning this has to be the next highest frequency. So we calculate that, right? But this has a carbon right here that has no hydrogens attached to it. So our n plus 1, this one has no neighbors. So this is just 1 plus 0, which is 1, meaning this is going to be a singlet. And, of course, it's a singlet, and that's exactly what we have right here, a singlet. Next is the one that's farthest away, right, the most upfield, lowest frequency. So this is going to be n plus 1. The 1 again is going to be the signal itself. 1 plus 2 is 3, meaning this is going to be a triplet, right? So that's 3, and we get a triplet right here, okay? So you should be able to draw these out and tell, like, what, because I believe that this was an exam question, okay? So this is the extra problem, and honestly, it's not bad. Like, it really isn't. First, just draw in your, wait, what's my note over there? Okay. First, just draw in your hydrogens. Okay. All the hydrogens, we're going to find out what the neighborings are. This, because it's attached to an OCH3, is hindered. Like, we can't, there's no neighbors. So this is just going to be a 1 plus 1, which is a 1 plus 0, which is going to be a singlet. This next one, 2 hydrogens attached to it. The oxygen is there, so it's going to only have these as its neighbors. So that's going to be 1 plus 2, which is 3, a triplet. Okay, same thing for the orange. It has, sorry, not the same thing. This is going to be the 1, so 1 plus 2 neighbors plus 2 neighbors. Okay, so that's what, 5? Yeah, 5. Next is we're going to calculate this one, okay? So these are the same, so we count it as 1, so it's going to be 1 plus its 2 neighbors. And again, this is just a carbon with no hydrogens attached, so it's just going to be 3, a triplet. Next, these, and again, they're the same because they have that relationship through the carbon bond. They are interchangeable, so they count as 1 altogether. And again, this one is also connected to this carbon, which has no hydrogens attached to it. So this is going to be another singlet because we do n plus 1, and this ends up being 1 plus 0, which is going to be a singlet. So now looking at this, which one would you think is going to be like our most de-shielded? Right, our most de-shielded, okay, yeah, I had to check. Our most de-shielded is going to be this one, right? Because this bond here is short, and this bond here with the carbon is long. Even though, and we have CH3s, right? So both of these on this side are CH3s, and we have oxygens, right? However, the oxygen that is connected to the carbon is a single bond. H and H is a single bond, meaning, and single bonds, remember, are longer. So it's going to take a longer amount of time for the electron density to be drawn through. However, on this side, we see the same thing. It's C, H, 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 double bonded to an oxygen. And that double bond is shorter, right? So here it takes, because let's say all the single bonds are 1 mile, right? It takes 2 miles to get over there. We're not going to add a mile for each of the hydrogens. But here, let's say this is half a mile, and this is a whole mile, because again, it's the single bond. It's going to take 1.5 miles to get the electron density to that oxygen. So that is why, because of that double bond being there, we say, and remember aldehydes and the rules on those, that is why we say that this side is going to be the most de-shielded. So this is going to end up being the most de-shielded. So this is first. So highest frequency, right? So now I'm going to erase these, and we're going to move on. Oh, Lord. Oh, my good golly. Hold on. Are you joking? Okay. Okay. What the heck? Okay, whatever. So let's move on, right? So we said that this is our highest frequency. Next, we can look at this one. So this one, again, is 2 hydrogens, right? So it's a CH2, and it is closest to the high electronegative oxygen, right? Because of that double bond. I'm not saying that just because of the double bond, it's higher electronegativity. I'm just saying that as a mechanism altogether, it's going to be drawing it faster, okay? And because, sorry, I'm so wrong. I'm sorry, but I can't re-record. This is going to be the second highest. This right here is going to be the first. Because of that difference in hydrogens. These two both are the same distance away from this oxygen. However, these two, because it has less hydrogen, it's more de-shielded, right? Because remember, the baby daddy, hold on. Yeah, so, because remember, the baby daddy is right here, right on the carbon. It's able to give its attention to half of them, meaning it's attracting like more electronegativity. It's attracting more electrons to itself better, right? Because of that carbon being right there with 2, as opposed to the carbon being there with 3 hydrogens, right? So because of that, this one is going to be the highest de-shielded because the carbon is pulling in both hydrogens easier than it would be pulling in 3 hydrogens, okay? So next, let's skip this one. Next, let's focus on this side. OCH3 versus CH2. They are the same distance from oxygen, right? They're separated by a single bond. So which one do you think would be the most deshielded? It would be this one, right? Because, again, that carbon hydrogen is really what matters. This is our CH bond, okay? This is our CH3 bond, okay? So our C bond is now, I don't know what other example to give. Maybe that example is not good. But borderline, carbon is pulling, right? It's pulling electron density towards itself. If it has 2 hydrogens, it can pull that density better because it's only dealing with 2. But if it has 3 hydrogens, then it's dealing with 3 and it's pulling it towards itself. And that is going to hinder it by a lot, right? So here we get 50%. For example, right, if I'm going to go to my calculator and do the math, if we have 100 divided by 2, that's 50. 100 divided by 3 is going to be 33. So here it's only getting 33% of electron density towards itself, whereas here it's getting 50% because it's only 2. So that's why, because this CH2 is getting so much more electron density drawn towards itself, it's going to be the most deshielded. So meaning that this is going to be, so this is first in line, this is second, this one is going to be third at the highest deshielded factor, right? And that means that this is going to be fourth, and this one is actually equal distances away from both, right? It's 1, 2, 3 carbons away from this. 1, 2, yeah, wait, what the heck? 1, 2, yeah, 2 carbons, 1, 2, 2 carbons away. So that's going to be right in the middle, okay? Oh yeah, sorry, not right in the middle. It's going to be dead last because it has no, like, it's not competing with anybody, okay? Like, it doesn't, it's neither above, no, this is 1, 2 bonds away. This is 1, 2, 3 bonds away. But even then, it's still going to end up last, okay? So this is first, and that's A. This is second, B, third, C, fourth, D, fifth, E. This one is confusing, okay? But what you really need to just understand is the fact that when there are more hydrogens, the hydrogens are going to end up being more shielded, okay? So more H, more shielded. Okay, and what does more shielded mean? It's going to have lower frequency. So when they are equidistant from one another, right, because these two were fighting to see which one was going to be more deshielded, right? It would be this one. Because there's less hydrogens, and so carbon can strongly pull those hydrogens. It's like a horse, right? If a horse is pulling 2 carts, it's going to go faster. But if a horse is pulling 3 carts, it's not going to go that fast. Okay? And yeah.